Hi everyone. In this lecture we're going to cover triple integrals over the cylindrical coordinate system. So the idea being we're used to dealing with the rectangular coordinate system, but in some cases it was more convenient to switch at least two of the variables of integration to polar coordinates. And that we're just going to make a little bit more formal in this section. So let's have a look at a brief example. Suppose we've got the problem of finding the centroid of the region bounded by the plane z equals 0, so the xy plane, and the paraboloid, given by that equation there. So that's this region that's sketched. We're trying to find the centroid, so the x center, the y center, and the z centers of mass, if you think of this as a constant density object or solid. And the way we do that is we pick a variable to integrate with respect to first. In this case, it would probably be the z first. So we do a z first integral. If we wanted to do a z first integral to do this, we would think, okay, for a given point in the footprint, we would then integrate along the z direction. And so we're integrating along this line segment, and then we'd let that arbitrary point xy that we just integrated above, we'd let that sweep out the region. And so with our integral, we're eventually going to have to integrate, we integrate z first, and then we're eventually going to have to sweep over the circular region. So this would, a z first integral would require us to consider a footprint, which is a disk of radius 3 in this case. And so for that we would use polar coordinates. And so there'd be a switch to polar coordinates at some point. So the idea is we'd use polar coordinates in the plane, and then the third variable would be the z variable itself. That gives rise to what we call the cylindrical coordinate system. The cylindrical coordinate system essentially just does that. It takes the x and y coordinates. Instead of using rectangular coordinates for those, we use polar coordinates. So we use polar coordinates for x and y. And our third variable, or our third coordinate, is given by z. In terms of a picture, it's essentially saying that for the x and y coordinates, we're going to use the polar coordinates. So down in the plane, if we look at a point in three-dimensional space, the projection down onto the xy plane, we're going to use polar coordinates to represent that. So it's given by the angle theta made with the positive x-axis. R is the distance to the pole or the origin. And then with the point in general, when you've got its z value also in the mix, that's raising it up to, or dropping it below the coordinate plane to whatever the value of z is. Then what r is really telling us is r is the distance that the point is. Distance p is to, in this case, it's the z-axis. So in the polar coordinate system, r is the distance to the pole or the origin of the point. But now that we're talking about this point living in space, in the cylindrical coordinate system, r is the distance the point is to the z-axis. Okay, and so let's get some practice then converting from polar to Cartesian. So for example, if we've got, so I said polar to Cartesian, but I meant cylindrical to Cartesian because we're in three-dimensional space. So cylindrical to Cartesian, we've got cylindrical coordinates 2, pi by 4, and 4, and we want to convert those to our Cartesian or rectangular coordinates. So let's get a feel for where this point's actually sitting. So it's got an angle of pi by 4. Maybe I'll just indicate that we're looking at our regular rectangular coordinate system, x, y, z. We got an angle of pi by 4. So there's our angle of pi by 4. That's our theta value. We're 2 units along that. And then that is raised up 4 units to the corresponding z value. So maybe I'll just sort of, with a little bit of perspective here, draw it coming down. So there's our z value of 4, and there's our point we're interested in. And that's the point that has those corresponding polar coordinates. So r theta z is equal to 2 pi by 4 and 4. And we'd like to find their Cartesian coordinates. So the thing to observe is that we've got the relationship up above. X is equal to r cos theta. Y is equal to r sine theta. So we can go ahead, and I will do these in parallel just because the calculations are virtually identical. It's r, which is 2, and then cos of pi by 4, and in the case of y, sine pi by 4, and cos and sine of pi by 4, they're both the same. They're 1 over root 2, so that's 2 times 1 over root 2, or 2 times 1 over root 2 for the y coordinate. And so we get values of root 2 and root 2 for x and y, and therefore our rectangular coordinates are given by x, y, z is equal to root 2, and 4. So that's how we get from our cylindrical coordinates to our rectangular coordinates. We can also go in reverse, given some rectangular coordinates, -1, 1, and 1, find the corresponding cylindrical coordinates. So these are our rectangular coordinates. X is equal to -1, y is equal to 1, z is equal to 1. We'd like to go ahead and find our cylindrical coordinates. That just means taking x and y values and converting them to polar coordinates. So we'll go ahead and jot those down. So there's our point in the xy plane. We'd like to find the angle, in this case our angle theta, and our corresponding distance r. R is equal to the square root of x squared plus y squared, or in other words root 2. That's our conversion from rectangular to polar coordinates for the r value. The theta value, tan of theta, that's equal to y over x, or -1, and that alone isn't enough to determine an angle. We also need to know that it's in quadrant 2. And so from that, we get that tangent of the angle is -1. It lives in quadrant 2, so theta is 3 pi by 4. In other words, pi by 4 is the reference angle. Maybe I'll just put that reference angle in there. So that's a pi by 4 reference angle. And since we're in quadrant 2, we know that the angle theta is 3 pi by 4. And so that's enough to tell us then that the cylindrical coordinates are given by r, theta, and z. R is root 2, theta is 3 pi by 4, and z is whatever it was 1. And so there's our cylindrical coordinates. So that's just an example of going back and forth between cylindrical coordinates and rectangular coordinates. Next, we can look at collections of points that satisfy a particular equation and look at how equations change based on the coordinates you're using. So for example, if we are looking at the rectangular coordinate system, the equation z equals x squared plus y squared, so it defines all the points x, y, and z that satisfy that. That's the paraboloid. What is the corresponding equation for a paraboloid in cylindrical coordinates? So we want to convert z is equal to x squared plus y squared to cylindrical coordinates. And so how can we do that? Well, we want to get rid of all the x's and y's and replace those with r's and thetas. And the first observation is, well, I've got an x squared and a y squared in my equation. So what I can do is I can replace x with what it is in terms of r and theta. So it's r cos theta. Y, what is it in terms of r and theta? It's r sine theta. And r squared cos squared, because if I square both of those factors, and then r plus r squared sine squared, the cos squared plus sine squared gives me a 1, so this just drops down and becomes a r squared. So in other words, z is equal to r squared is the equation of this paraboloid. Okay, so that's the equation of this paraboloid in cylindrical coordinates. Now if you're wanting to graph things, you could go to a graphing utility. And the thing to note, I just want to point out that with math3d.org, when you click on your add object, you've got your explicit surface, so that's what's drawn here, z equals x squared minus y squared. But you also have the ability to plot an explicit surface in polar coordinates. So explicit surface just means it's going to be z is equal to an expression in polar coordinates, r and theta. So this is essentially cylindrical coordinates. So I'll switch to that one. So I brought up a explicit surface in polar coordinates, and for us, the one we just calculated, the paraboloid has an equation z equals r squared, so if we put an r squared in here, we get exactly that. There's our paraboloid. And now, the way we sketched it was we sketched it in cylindrical coordinates using the equation z equals r squared, rather than rectangular coordinates, z equals x squared plus y squared. Okay, so we're able to take equations that define surfaces and convert those into the new coordinate systems using the new variables. We could go the opposite direction as well. Suppose we have a surface whose equation in cylindrical coordinates is r equals 2. What is that surface? So what would that surface be? Well, one way to do this is to say the surface is the collection of all points given by their cylindrical coordinates r, theta, z, such that r is equal to 2, theta is anything between 0 and 2 pi, and z can be any real number. There's no restrictions on that. So that's what that equation says. What is the set of all points that satisfy r equals 2? It's this, the set of all r, theta, z, where r is 2, theta is any value between 0 and 2 pi, and z is equal to r. And so that means that we can even write it more simply, that it's 2 theta z, such that theta is between 0 and 2 pi, and z is any real number. And what is this? Well, in polar coordinates, we know what that is. In the plane, this is the set of all points whose distance 2 from the pole. So this is a circle of radius 2 in the plane. And then we've got z can be anything. So it's basically this circle of radius 2 with any z value allowed. And so it's a cylinder. So this becomes a cylinder. So we can sketch it out here. So I'll sketch it in a different color. So it looks like this. And so on all the way up. So it's a cylinder of, in this case, of radius 2. An alternative way we could get this, so alternate, this was just looking exactly at what points are that make up this surface, and we see that it's got to be all the points that live on this cylinder. An alternative way to do this is to say, well, work right from the equation. R is equal to 2. Okay, let's convert. Convert to rectangular coordinates. That means I'm going to take all of the variables and put in place, replace them with x's and y's and so on. Well, in this case, r is related to x and y via x squared plus y squared is r squared. So r can be replaced with the square root of x squared plus y squared, and that's equal to 2. Or in other words, x squared plus y squared is equal to 4. So that's our Cartesian equation for the same surface. And we know that this is a cylinder of radius 2. So this example, it was chosen specifically for a reason, because it illustrates where the word cylindrical comes from in the cylindrical coordinate system. The rectangular coordinate system has the property that when you take equations like one of the variables equal to a constant, so x equals a constant, or y equals a constant, or z equals a constant, and you plot all those kinds of lines, or planes, x equals a constant, y equals a constant, z equals a constant, then what you get is all these planes that sort of chop up your region into rectangular boxes. And so that's where the word rectangular is coming from in our rectangular coordinate system. If we look at the corresponding equations here. So r equals a constant. Well, we're just seeing that that's a cylinder now. So r equals a constant is a cylinder. So one of the basic variables in that coordinate system, when you set it equals a constant and look at the corresponding surface, it makes a cylinder. So this is where the term cylindrical coordinate system comes from, because the basic shapes, the basic surfaces we get in this coordinate system are cylinders. So if you're ever dealing with something that involves a cylinder, cylindrical coordinates are probably the best way to represent it, because the equations become so simple to represent that object. R is equal to a constant, and you've got your cylinder. All right, so that's it for the first part of this lecture, just introducing the coordinate system. I'm going to do 2 more videos. The next one is the introduction of triple integrals in cylindrical coordinate systems, and we'll do 1 example, and then the third video will be a second example. So we'll see you in the next video.